It's my great pleasure to welcome Mérouane Debbah after the nice talk yesterday of Gerhard Fettweis on 5G. Today it's another big guy of the 5G who will give this plenary talk. So let me just introduce Mérouane. So Professor Mérouane Debbah get his PhD from École Normale Supérieure de Cachan in France. From 2003 to 2007, he was assistant professor in Sophia Antipolis Institute Eurecom, and then from 2007 is a full professor at Supélec in France and holder of the Alcatel-Lucent chair on flexible radio, and is also recipient of the ERC grant MORE, meaning Advanced Mathematical Tools for Complex Network Engineering. He received many Best Paper awards, and in 2001 he received the famous prize, the IEEE Glavieux Prize Award. So it's my great pleasure to welcome Mérouane for this talk on the 5G energy efficient wireless design.
Okay, thanks. So I don't know. Okay, so I think I have to talk here because the thing doesn't work that well. So it should be fine. Okay, great. Okay, so first of all, thanks for coming this morning. I think the weather is excellent, and you should have gone to the beach and enjoyed the time there. But I'm very happy that you came to listen to my talk, especially as I had to prepare it. So at least there's something, a bit of meat for you to listen to. So my talk is going to be about 5G energy efficient wireless design. It has been mostly made by one of my postdocs, Emil Bjornsson, who's now moved to Linköping University and has got an assistant professorship there, and Luca Sanguinetti, who has a Marie Curie fellowship and who's working also in my team within Supélec. So as far as I'm concerned, you have to know that I'm a specialist of random matrix theory, and I've been working since 7 years at Supélec through an Alcatel-Lucent chair on flexible radio around the topics of random matrix theory applied to wireless communication, as far as I would say asymptotic design is concerned. And we've been using that tool in a very efficient manner to understand better how 5G massive MIMO small cell networks could be deployed. Another third of my activity these last 7 years have been around game theory, applying tools for, I would say, defining self-learning algorithms for small cell networks. Another 1/3 of my activity has been on the use of what we call software-defined radio tools to be able to implement those things, and we've developed some cards called SDR cards. Now I have to make a bit of publicity. It turns out that starting September, I'll be joining Huawei and opening their French R&D research center, which will be around the mathematical and algorithmic science lab. And the objective of that lab is to provide some new ideas around 5G using mathematical tools. So we're looking to recruit 70 top mathematical experts in that field. So if some of you are interested to join in, I'll be very happy, because we have to fill those positions by the end of the year, meaning end of 2014. The topics that we're looking at for your information and we have identified are these topics that you see behind. So we're looking at experts using random matrix theory, free probability theory, stochastic geometry, discrete mathematics, statistics, game theory, mean field theory, information theory, signal processing, queuing theory, estimation theory, decision theory, probability theory, optimization theory, statistical mechanics, factor graphs, control theory, learning theory, partial differential equations theory, and optimal transport theory. Now you can ask me why we're doing that. Well, basically, it turns out that in 5G, and that's something that Bell Labs has also been doing since the late 1880s, is that you cannot define new, I'd say, algorithms and new IDs just by trial and error. And so mathematics is at the foundation of developing new IDs, and that's something that Bell Labs and then AT&T found useful by bringing the top experts in the field to develop the networks we know that are being developed right now. The reason fundamentally why I also insist, and you'll see also in my talks, that in 5G there's a lot of mathematics, is that we're quite stuck with the Moore's law at the moment. And if you look at how the progress of the Moore's law has been used. It's been almost used up, and we can't do better anymore. And it turns out that there's been some studies showing that at the heart of 5G networks, if you look at how the daily traffic in terms of increase is going to go, some people talk about a 100 factor, others 1,000 factor, depends on the talks you've been listening. Well, if you start counting on how you can save energy per bit through Moore's law, improve energy efficiency, you'll see that the fact that you use algorithms and less computation has a big part of it. And that's going to be one of the big things which are going to be there in 5G. And a lot of people are investing in what we call tools for 5G. And that's one of the reasons at the heart of this center that we're developing in Paris. And I hope we'll have collaboration with you guys around that lab. Okay. Now I'm going to start my talk about this 5G. So first of all, I'm going to do some introduction about what is 5G, what people are looking at, and what we're aiming. And then there's going to be 4 parts. The first part is going to be about what we call the problem formulation, system model, what kind of metrics we're dealing with, energy efficiency, rate, power consumption, what are we talking about. And the part 2 is going to be very interesting because we're going to optimize the network based on energy efficiency. We're going to look at how to design a clean slate approach of, I would say, 5G based on this metric, which we call energy efficiency. And you'll see that massive MIMO will appear immediately as one of the solutions when you start doing the maths behind. So it's not something that you impose, it's just that by doing the maths behind, then massive MIMO appears as one of the options to be able to provide that energy efficiency gains that you're looking at. Then, of course, we're going to talk about the solution that we're going to find, which is massive MIMO, how it is, the main properties and the optimal IDs. And then we're going to look at what's at the heart and one of the biggest problems in 5G, what we call multi-objective network optimization. As you know, there's a lot of constraints that we're looking at in 5G. It's not anymore about increasing rates. There's a lot of different criteria. And it turns out that exactly in the same manner, mathematics will appear as one of the tools to be able to find a solution to that. Okay? Okay, I think you saw many talks around these things saying that, of course, there's a rapid traffic growth in the next years. A lot of factors, depends on the studies that have been made. Either it's Gartner, Cisco here that I brought here, showing it how you have this exponential increase in terms of traffic, and people are doing extrapolations, and that's one of the reasons we're looking at a new technology willing to sustain those increases in terms of traffic. Now, it turns out also that there's what we call Martin-Cooper's law that shows also how the traffic and data connections are increasing every, I would say, 2.5 years. And if you saw the Cooper's law, there's around a 32% increase per year. And with the new predictions, you'll have something around 61% per year, which shows you also that we're trying to aim something new. Okay. Now, if you look at how things have been designed before, usually people have been looking at what we call higher data rates, and that's at the heart of 2G. 2G was mostly voice, but let's say 3G and 4G then having a higher data rate. It turns out, of course, that if you look at that, the implementation and design was basically done by looking at how signal propagation was going on. And if you look at the way signal propagation is going on, then of course you have here at the heart of base station, and here you have cell edge. And then we had, as you know, in these 4G scenarios, a lot of problems in coping with people at the cell edge because these guys didn't have the right rates to do it. It turns out also that if you look at the spatial distribution of users, when you look at a network, the majority, unfortunately, of users are at the cell edge. Of course, they're not physically there. It's people who are connected. And you have to know that why a lot of users are at the cell edge in general is just because if you have a bad connection, then in general you stay there and you take that resource and you stay for long. So if you take a snapshot of a given cell, then you have some people at the cell edge more often than near the base station because people are near the base station just take the traffic and they just go. Okay? So that's also something that you need to incorporate in your modeling whenever you start taking into account the user distribution in your network. Okay. Now, that was until 4G. What is 5G? Now, if you look at 5G, well, there are different expectations from 4G. It turns out that there's still some design objectives that are being defined at the moment, but these things, there's a lot of consensus around them. Increasing the average rate, even increasing the average area rate, having a number of active devices which increases, and you're having what we call also an energy efficient metric. So basically, instead of having just the increase of high data rate, it turns out that people are trying to cope with all these different combination of metrics and trying to impose a new clean slate design of the network based on these metrics there. Okay. Now, if you have that, how should you start? Well, you've been going through a lot of, I would say, plenary talks and overview articles around 5G, saying what it should be. But however, we still lack some fundamental, I would say, reasoning around that thing. Okay. So here, what I did is just recall the different objectives that people have imposed for 5G: higher user data rates, higher area throughput, great scalability, number of connected devices, higher reliability and lower latency, better coverage and with more uniform user rates, and improved energy efficiency. Now, if you want to incorporate a clean slate design taking into account all these metrics, it's a bit complicated, okay? And often these metrics are conflicting, meaning you cannot have a win-win situation for all the things. So my talk will start step by step. The first thing I'll do is just look at one of the criteria, which is higher user data rate, and look at what is the clean slate design that I have when I just impose a higher user data rate. And then I'll impose 2, and then I'll impose 3, and then we'll go forward until we start imposing all these constraints, okay? So if you start imposing the first one, well, that's going back into, I would say, the 4G constraint that we put in just having higher user data rate, okay? Now, if you look and you want to increase the data rate, it turns out that if you look at how, and these have been taken also by, these graphs have been taken by also some studies made by companies, and you look at how the efficiency of networks have been increasing, it turns out that the biggest efficiency that you have been gaining is through what we call spatial reuse, having more antennas. Okay? And it turns out that, of course, one way of increasing and getting more and more data rate is increasing the number of antennas per unit area. Now, the question I'm going to ask is very simple, is that suppose that you have 400 antennas to deploy, how would you deploy these 400 antennas? Would you put one base station with 400 antennas, 2 base stations with 200 antennas, 3 base stations, and you start doing like that until you have 4 base stations with 1 antenna each? Okay? This goes back, of course, to something that Bell Labs already in 2010 had as a roadmap, is considering to deploy a network based on a given DNA. And that DNA was called at that time the cube, or called the light radio, which was basically to have one component of a network and be able to construct your network in a Lego manner, where you start constructing by boxes and putting that. It turns out that it didn't work. They're still trying to make it work, because as you know, when you start doing things with different components, then you cannot be energy efficient, okay? You have many amplifiers. It's better to construct a base station with 4 antennas from scratch than just to add 4 elements and construct that base station with 4 antennas. But still, the idea is there for a lot of people doing research, is to say, okay, if I had one component, which is the DNA of the network, how could I construct it in a Lego manner? But in any case, let's go back to my question and make what I call a thought experiment. Consider an infinite large network of randomly uniformly distributed base station and user terminals. What would be better, 2 more base stations or 2 more antennas per base station? So to go back to my example, I have 16 antennas, 1 base station with 16 antennas, 2 base stations with 8 antennas, 4 base stations with 4 antennas, and you're going like that. And we'll see what's the results we're going to get, or what are the results we're going to get. So for that, let's go on the downlink or uplink. This is just for an example. I look at the downlink, and I suppose that my users have 1 antenna. And this is what I call the desired signal coming from the closest base station to the user. This is the path loss, okay? This is the fading, and this is the transmitted signal, plus the interference coming from the other antennas. Be careful, if you have 1 base station with 16 antennas, you don't have this thing, because you do joint precoding with your 16 antennas. If you have 2 base stations with 8 antennas, then you have here, of course, a vector here, which is 8, because you have 8 antennas. And here, this is the interference coming from the other 8. Okay? So this is scalable depending on the things. So what I do so that's exactly what the receiver is getting. And of course, I'm going to do some kind of pre-coding in the downlink for that. Okay? I have a channel here, which is a fast fading channel. It's zero mean and a covariance of identity. Ri is the distance to the ith closest base station. And P here, is the power, or the average transmit power. Be careful, this model is a bit wrong, but we started with that. Why? Because, of course, the statistics should depend on the distance. Okay? If you have a small cell scenario, it's impossible that your relay if you're very close to the base station, your line of sight. So basically, of course, you can tweak that. We did that. But it's mainly a constructed model and a tow example, okay? But we've been looking in literature if there's models which takes into account the fact that the statistics of your channel change with path loss, which means here that H here should depend on R. Okay, for everybody, but the majority of examples are not taking that way. So the assumption is that we have an infinite large network of uniformly randomly distributed base station and unit terminals with density lambda BS and lambda UT. Okay, that's the density of base stations and unit terminals. I have single antennas unit terminals and n antennas per base station. And each unit terminal is served by its closest base station. It's a distance path loss factor with path loss exponent alpha here, superior to 2. And I suppose that I have a total bandwidth W reused in each cell. Okay? Of course, you can do some kind of reuse factor. I did it here, but for the example, don't care. We suppose that we have a reuse factor of 1. Okay? Now, I'm going to use what we call a zero-force sync recorder, but you can use something else. It's not important. I called kappa, which is the lambda UT divided by lambda UBS. The number of unit terminals need to be served by each base station on average. Okay? The total bandwidth W is divided into L subbands. This is for FDM, but suppose here that you have only one carrier. It's not important. And K here is equal to kappa divided by L. But since you suppose that L is equal 1, because we're not doing some kind of frequency reuse or FDM, you suppose that you have kappa, K equal kappa. The transmit vector of base station I, well, it's xi. As you can see here, you divide by the number of users that each base station serves. And here you have a precoder which serves the number of users you're going to serve in your cell, which is k here. Okay? SIK is the message determined for user terminal k from base station I, and WIK here is the zero-forcing beamforming vector. Okay? Now you look at the downlink SINR. So the downlink SINR is the energy to the closest base station. This is interference plus the noise, which I rewrite this way here. Okay, S is this thing, GI is this thing here, and K over P. So of course, if you have one base station with 16 antennas, then this factor does not exist, okay, because you don't have interference. Okay, I look at one metric, which is the coverage probability. I want to have a target rate, and the higher rate I can have is the best, which I call P coverage, which is the property that gamma is superior to T. And I define also the average throughput, which is W divided by L times expectation of log 1 plus gamma, which you can rewrite in this way, by the way. Okay? Now, of course, my goal is to have an expression of this thing and be able to analyze things. It turns out that this expression here is quite complicated, and using stochastic geometry tools, you can have an explicit expression of this average rate here. So for the statistics that you have here, S here, which is your channel plus the precoder, well, it's a gamma distribution with a certain numbers of degrees of freedom that you can write in an explicit manner, and that you can do. It turns out that in fact it's even easier. In literature, you have these expressions. You just need to combine and find them. You don't have to write things very complicated in a very complicated manner. It's a combination of results from Bacelli and Andrews, and you can have an explicit expression of the coverage. Okay, by combining these expressions, you can get them. The most important thing is this. The most important thing is this, because if you look at the density of user terminals, which is 16, I consider that I have a constant transmit power density, which is the same, meaning if I have 16 antennas, either one base station or things, it's the same power that I radiate, okay? The number of base station n is lambda UT divided by lambda BS. I take a path loss exponent alpha equal 4, and this is the number of user terminals which are simultaneously served on each band. Okay, K equal lambda UT divided by lambda BS times L. What's important is this first line here, when I use one carrier. If you have one base station with 16 antennas, this is the spectral efficiency you get. If you have 16 base stations with one antenna, this is the spectral efficiency you get. So it means that small cells provide you a much higher data rate than massive MIMO, in this case here. A lot of antennas in your base station. So if you're only interested in average rate, okay, increasing your average rate, even if you have full interference of nearby, okay, small cells, you still get a factor of 3. Now, of course, if you do some kind of coordinated approach, meaning that you start doing some kind of comp technique with these small cells and coordinating, you can even have better. But already tells you that if you want to do deployment and you have a number of antennas which you want to deploy in a Lego manner, you just deploy them like that, it's much better to distribute them randomly than to put the 16 antennas on one spot. Okay? If you're interested, of course, in having an average throughput per user terminal which increases. Okay, you're not interested in the other metrics. Okay. You have to know that already in the late 70s, there's a nice book called Stellar Dreams and Cordless Nightmares. I encourage you to read it. It's called Life at Bell Labs, Interesting Time, by Richard Frankel, which was a researcher there. Now he took his retirement. He's a professor in the US. And you have to know that already in around the 70s, Bell Labs had already the ideas of small cells and found already that that's one of the best solutions you can have. You see here, this is taken from one of the pages of the book. By 1976, the time had come to prove that our many claims could be turned into a practical system. Small cell coverage over a large service area would require hundreds of cells and cost hundreds of millions of dollars. Of course, at that time, the big problem was the cost of deploying small cells. Now, of course, we're aiming, because of the fact that the cost of one box, let's say, has decreased, that in fact we can deploy these things in a costly manner. But at that time, one of the main reasons was the cost. Of course, if you start deploying small cells without the backhauling, it costs you a lot of money. So we applied for permission to conduct 2 separate trials. A large cell market trial in Chicago would provide realistic service to more than 2,000 customers, while a small cell testbed in New York, New Jersey, would demonstrate that the small cells could provide good service in the presence of nearby interference. In combination, these trials would provide a complete demonstration of our system. So what you have here is exactly the framework of what we call macro cell plus small cell called HETNET, a combination of both, where macro cell provide coverage and small cell provide capacity. Okay? And at that time, even taking into account what we call nearby interference, meaning the small cells providing that interference, it's something that could still work. Okay? Of course, at that time, the big player was Motorola, and Motorola, of course, came into the play, and Motorola objected to our proposal as inadequate. Since neither the trial in Chicago nor the testbed in New York demonstrated fully the developed small cell system, Chicago, they argued, used very large cells, while New York was only a partial grid of small cells. Since the demonstration of small cells over a large area network was clear and practical, that's impossible to do because of the cost, as I told you, we were confident that the FCC would see Motorola's objections for what they were, another smokescreen intended to delay progress. As it turned out, our fate was misplaced, and in fact, FCC went into the small cell, into the macro cell, scenario, and pushed for the Motorola option. You have to know that they did some trials. This is a van taken one in the picture. They took some vans, put some small cells to do a very small cell grid where they did some trials to prove that their claims that it worked. Okay. Now, of course, my question is not about 4G and how to increase 4G, which is through small cells, because if you're interested only in average throughput, that's what you should do. Okay, irrespective of cost, other metrics, just average throughput. My big question now, of course, is to take into account all these metrics. And now, of course, what I'm going to do is try to take into account having a better coverage with more uniform user rate and improve the energy efficiency. Okay, these two. And see what kind of solution we get when we add these 2 metrics in terms of design. Okay? Okay. So, of course, taking these 2 metrics is something that Bell Labs also looked at in 2009. And in fact, it's something that I think they didn't come up with a solution yet, because one of the goals, as you know, in 2009 was to develop a consortium called Green Touch to reduce by a factor of 1,000 the energy consumption of networks. Okay, and we're already now in 2015. I mean, at least in a couple of months, and we don't have, especially a solution with a 1,000 factor reduction for that. And it turns out that the solution that the guys in Green Touch had come up with is also a combination in 2009 of massive MIMO and small cells. That was one of the solutions which was thought to be the one to reduce the energy consumption. And as you can see, this is a graph taken from one of the presentation where they looked at showing how the different components could improve the energy efficiency. Small cells provide the best ratio for transmit to receive power. Backhaul permitting allow for tremendous increase in capacity per unit area and coverage, increasing bandwidth, and for macro cell, each doubling of antennas reduced transmit energy by 3 dB. Okay, that combination, they came up and said, okay, if we do a very condensed scenario, we will go with a cell radius of 10 meters, then that's the way to go to a 1,000 factor reduction, which is still a problem. But for me, I want to go back to the basics and see what kind of solution we get. So let me define what we call the energy efficiency and look at this metric where we, at the same time, we want to increase the average sum rate and reduce the power consumption. I'm not saying that this is the best way, because why should I increase the ratio when I had 2 metrics? Why should I put it in a ratio? I'll explain this at the end, by the way. Okay, there's no reason why I should define that way when I define these two metrics at the same time. Why should I maximize the ratio? But I'll explain afterwards at the end how you do some kind of optimization when you have different metrics. So the conventional academic approaches is to maximize rates with fixed power or to minimize transmit power for fixed rates. Here, of course, what we want to do is try to balance both and balance rates and power consumption to take into account for overhead signaling and circuit power. Okay, so let me first consider what I call the achievable rate per active users. I define the bandwidth times log 1 plus here what I call the SINR. Okay, and that's going to be the metric which is going to be at the numerator. Okay. Now, I'm going to do a clean slate design of a network based on that energy efficiency. I consider, first of all, a single cell. In the multi-cell, things will change also, where I have one base station with M antennas, you see here. Geometry, I have a random distribution for user location and path losses. And multiple users, I'll have to pick k users randomly and serve them with some rate R, which is this constant rate I'm looking at. Okay? So my goal here is to find M, K, and R. What is the optimum M, the number of antennas I have to use in a system? How many optimal users I have to serve? And what is the rate I should give them to maximize the energy efficiency? Okay? And of course, if possible, not do it numerically, get an exact expression of that to be able to do the things rightly. So what I'm going to consider is the TDD case. If you do FDD case, it's something else, and it's more difficult, as you know. And already in massive MIMO, FDD is already posing some important problems. Uplink and downlink in TDD are separated in time. I look, there is an uplink fraction time, which I call here this tau uplink, and downlink fraction downlink. Okay, this is the time of the uplink, and this is the time of the downlink, where I use pilots. I have a bandwidth of B channel uses per second. This channel stays fixed for U channel uses, which is current time block. This is the time it stays constant. And determines how often we send pilot signals to estimate the channel. This is the time I'm going to use to estimate, and the time I'm going to use to estimate the channel in the uplink and downlink. First of all, I'm going to assume that once I dedicate some time here and here, I have perfect estimation of the channel. But then, of course, I'm going to take into account those discrepancies in terms of non-perfect CSI. Same thing. To do it, I have a channel between base station and user K is HK, relay fading HK, and the channel variances lambda K, which are related to the user position, to the distance pass loss, are random variables with the PDF f of lambda. Be careful, the model is still wrong, because HK here, the 0 here, or I'd say the mean, sorry, should depend on lambda K. Okay? If the variance is if you have a distant path loss which is very small, then of course you can't be line of sight. Your statistics change. I look at the uplink transmission. User K transmits signal SK with power P uplink, and the received signal at the base station is Y equal HK SK plus all the other users which are transmitting at the same time. Okay? I just put here. Plus, of course, you have the noise here. Okay. Now, of course, the base station here does some kind of signal processing, okay? And this is what I call the received beamforming vector JK. It can be a match filter. It can be whatever you want. For the moment, I keep it general. The SINR in that case, in the uplink, is expectation of the signal of interest plus interference plus noise, which you can rewrite this way because this goes out, it's PK. And here you have this PI uplink plus sigma squared JK, where here, this is the received beamforming, okay? Let me look at the downlink now. Same thing in the downlink. I took the same model. Base station transmits DK to user K with power, this power here. Use spatial diversity by beamforming vector VK. Use another beamforming vector. The received signal at user K is HK, the beamforming vector, which is normalized to keep the energy. Okay? Plus the interference from that is sent to, or the signal which is sent to all the other users, plus NK. This is the signal of interest. And the SINR in the downlink has an expression of this form here. Now, my design parameter is to make sure that every user has a fixed rate R. So for all user K in the uplink, B log 1 plus SINR uplink. And for all users in the downlink, B log 1 plus SINR in the downlink. Okay? And my goal is to select the beamforming vector jk and vk and adapt the transmit power pk and downlink power and uplink power, okay? Now, if you do that, no problem, you can solve it. If you fix the target rates that you need for the users, but for the moment I'm not looking at energy efficiency, you have to solve a certain number of equations. Because here this is 2r to the power of b, and you need just to make sure that the power are solvable of this equation here. And you have a couple of linear equation transmit power, and you can solve that by Gaussian elimination to find the powers, the beamforming vectors, and you go on like that. It turns out that if you're interested only in transmit power, okay, and you suppose that the downlink beamformer and the receive beamformer are the same, you can compute easily the transmit power. And the transmit power is B expectation of sigma square, vector 1, transpose emission, D minus 1, vector 1. Okay, this is the power that you're going to use. If it's just a transmit power for a fixed target rate. If you fix the target rates, this is the power that you're going to use, where D here is a matrix for which each of the components can be written in this form here. Okay, so you can have exactly the energy consumed if you target some rates. Okay, now what I did here is, of course, I did the optimal power allocation for fixed beamforming vectors. I fixed them, okay? Meaning here I used GK equal VK, and GK or VK can be anything. Okay, is that clear? Now, of course, our goal in general is also to optimize the beamforming vectors. So, of course, if you fix the beamforming vectors, you have many ways to do it. Either you can use the maximum ratio transmission or reception, meaning G and V is equal to H. You can use some kind of zero forcing beamforming, and in this case, you use this thing here. Or you can also find the optimal beamforming vector, which has this structure here, okay? And where you need to optimize this P numerically. This is much more complicated, okay? Because this PU here is an iterative process to optimize. Okay. Now, in the case of the zero forcing, if I use the zero forcing, my expression of transmit power that I had here, you see, can be computed explicitly. Okay, if you want an explicit expression, you can compute it explicitly. In this case, the D matrix has a nice expression. And it turns out that the transmit power also has a nice expression, which is of this form here. B sigma square 2R, where the rate is the rate that you want to target for users, minus 1, K, M minus K, expectation of 1 over lambda, where lambda is the variances of user positions, you remember? So you have the transmit power that you're going to use in your network if you do that. So I call here, by the way, alpha. The term alpha here is this thing here. 2 to the power R divided by B minus 1, M minus K. This is the alpha that I'm putting here. So of course, if you want to look at the transmit power with zero forcing, this is the target rate, and this is the power that you're going to use to serve the user, which depends on the user location here, the number of users, sigma square, B, and a factor here which depends on the rate. Okay, so you can have an explicit expression. So of course, my goal here, is to maximize the energy efficiency. It's not about transmit power or just rate. It's the energy efficiency. To do that, it's much more complicated because you need a model of what we call the energy consumption of everything. Okay, just not transmit power. So what consumes power, it's not only the radiated power, their secret signal processing backhaul must be specified as function of M, K, and R. So first of all, you take into account the power amplifiers. So the power amplifiers have some efficiency in the uplink and downlink, each one of them. The average inefficiency of those power amplifier, well, it's the time you use them in the uplink divided by the efficiency in the uplink, and the time you use them in the downlink by the efficiency in the downlink, which gives you 1 over tau. So the power transmissions, taking into account the efficiency taking into account the power amplifier, is P transmit divided by eta. Then you have also what we call the active transceiver chains. You have a fixed power here, control signals, oscillators at base station standby, which I call P-fix. You have the PBS, which is called the circuit power per base station antennas. How many you have? You have M, so I put M times PBS. You have also the circuit power per user, which corresponds to the oscillator, converters, mixed filters at the user equipment, K times PUE. Okay? Then you have also some time spent for signal processing, channel estimation, and all these things. So here, that's what I put. You have in signal processing the number of the efficiency of the arithmetic operations at the base station, and this is the efficiency of the arithmetic operations at the user equipment. They have different, of course, efficiencies. In terms of channel estimation, you have B divided by U. U, you remember, is the number of time symbols. B is the bandwidth, okay? And then here, this is the operations that you have at the base station, and this is the number of operations that you have at user equipment, taking into account the number of antennas and the number of terminals which are transmitting, and here also the number of terminals, okay? Tau ULK and Tau UL and Tau DL is the time you're spending in downlink and uplink. Then you have also what we call the linear processing that you're doing, for in the case where G equals V, that's B divided by U, the number of operation that you're doing for beamforming, plus also this term here, okay? So depending on the time of beamforming that you're doing, the number of operation is 3mk for maximum ratio transmission. Zero forcing beamforming, you can also compute them. And also for the optimal case, you can also compute them here, okay? And here, you have also the operation that you're using for doing the beamforming during the transmission. This is why I take off here the time of training and estimation here, okay? Okay, and then you have also some energy which is consumed for coding and decoding, okay? Energy for coding data per bit, PCOD, and this is the energy for decoding data per bit, which gives you a given sum rate which takes into account all the components here with the coding, decoding, and the system. And then you have also some backhaul signaling that I put here, which is P of load independent backhaul power, and BBT here is the energy for sending data over backhaul per bit. Okay, and since you have R rate, that's the total you get. Okay. At the end, what you get is, of course, not only the P transmit power that you saw at the beginning that I computed for the zero forcing and for every kind of beamforming, but the whole expression which takes into account the active users. Be careful. Because usually when you take this thing into account, you don't take into account the number of antennas which are consuming and all these factors. So if I sum them all, that's the generic power model which you come and which you take into account all the components. All these factors here are tabulated in tables, by the way, you have to know. Okay, so these are tabulated. You just take the green touch deliverable, and you get all these coefficients and numbers that you can have there. Okay. So here you have to transmit with amplifiers, the fixed power, the circuit power per transceiver chain, the cost of signal processing, and the coding, decoding backhaul. Okay, all the components. Now that you have all these things, our goal now is to maximize the energy efficiency, which is one of the metrics in 5G, taking into account these two, the rate, the average rate and things. So the average rate is here, as you can see, and that's exactly the energy that you're consuming. And to maximize this, M, K, and R. Okay? Now, with zero forcing, as you remember, we had a closed form for exactly the power transmission. Okay, and if I look at the zero forcing, the problem gets back to this thing here. Maximize M, K, and alpha, where alpha is something which was related to the rate. Okay, either you maximize the rate or this alpha here, because these things are fixed. Okay. Now, why did I use such a complicated model and went into all the details? Well, for a simple reason, is that if you look at the literature, and there's been a lot of results in the literature which have been wrong, is that people do the following. They consider, to maximize the energy efficiency, the transmit power, the rate, divided by the power transmission plus a fixed secret power. They just take a fixed secret power, then all the things is fixed. Well, if you do that, if the number of antennas goes to infinity, then the rate here in the numerator goes to infinity, and thus energy efficiency goes to infinity. You have a problem when you have just a fixed power of consumption, which doesn't take into account the number of active users in your network. Okay? Same thing, if you neglect the energy which is consumed in power overhead, pilot overhead, and signal processing, the same thing happens. There's been a lot of asymptotic results used also by Tom, where you make the number of users go to infinity, the number of antennas goes to infinity, but the ratio goes to constant, and you fall into the same problem, caveat. Meaning that when you do this asymptotic setting, the rate goes to infinity and the energy efficiency goes to infinity. So it just tells you increase the number of antennas to an infinite number, and you'll decrease every time by 3 dB, by 3 dB, 3 dB, and that's the option. Okay? So you can't take into account this thing which is fixed. You need to take into account all the components. Okay. Let me now do the optimization. So my goal now that I have the metric, I spent a bit of time defining the metric. You see here? Sorry, this one. Okay, let me now optimize it. So I need to optimize the number of antennas, optimize the number of active users, and optimize the transmit power alpha, which is related to the rate, by the way. Okay, and I'm going to do it for zero forcing processing, and for the others, I'm going to do it in a numerical manner because I can't have an expression. It turns out that to do that, you need to define what we call a lumbar function, and the lumbar function is solution of a certain equation called Wx, exponential Wx equal x. That's something quite known, and it satisfies some constraints here, as you can see, but this function will appear many times. Just to let you know, this function is called the lumbar function. Okay? Now to solve it, you need a bit of optimization background in mathematics. How to solve the optimization problem? Simple if the function is nice. Okay? That you know. We'll need the definition of what we call quasi-concave function and a concave. For any 2 points that you have on the graph of the function, the line between the 2 points is below the graph here. Okay? Property goes up and down. An example, minus x, log x, stuff like that. Okay, maximization of a quasi-concave function is easy. This is why I'm using it right now, because then you just have to derive it and you go on. So, okay. It turns out that if you want to maximize the energy efficiency with zero forcing, uplink and downlink, then you can show that there's an optimum number of antennas that you should use, m star. Not going to infinity, there's an optimum number of antennas, and that number of antennas is given by this expression here, where here you have the lumbar function. Okay? What it tells you is that, of course, the number of antennas increases with circuit coefficients, independent of m, decreases with circuit coefficients multiplied with m, and independent of cost of coding, decoding backhaul, and increases with power alpha, as alpha divided by log alpha. Okay? Same thing, there's an optimum number, optimal power that you should use in terms of transmission or the rate that you'll target. Okay? Which is given by alpha star, and it's also something that you can get explicitly here. Finally, same thing, the number of active users that you should use, okay, can be also given in an explicit manner. It's a quasi-concave function of k, but the only problem is that it's a solution of a certain equation that you need to solve numerically. But you have a certain equation where k is solution of. Okay? Let me skip this because I want to go just back to the result. Okay? And show you now the result, that what you get. So I took here a circle cell with radius 250 meters, uniform user distribution, uncorrelated Rayleigh fading, and a typical 3GPP path loss model. And I took all the coefficients here that you can find in tables, meaning here the power amplifier efficiency at the base station, the power efficiency at the user equipment, fraction of uplink transmission, and I took all these coefficients. What the story tells you is that if you want to do an optimal single cell design, using zero forcing beamforming, but you push to zero forcing beamforming. I didn't do the optimal even with the optimal processor. The optimal thing you can do is a massive MIMO setting, in the sense that you need to have an excess number of antennas, and the number of excess is exactly 165. K is equal 104, and alpha equals 0.87, which means that massive MIMO appears immediately as a solution for the energy efficiency metric, if you want to optimize it. Okay? So what you have to do is, of course, multi-user MIMO with many antennas and serving also many users, 165, 104. And here what you get is also a target rate of 64 QAM. Now, if you do the optimal beamforming, same setting, what you get is M equal 145 and K equal 95. Okay? Here it's also a massive MIMO setting with 64 QAM. The only problem is that, of course, you cannot have an explicit expression of this optimal beamformer, and it's an iterative process, as you remember. Okay, but same thing, it appears immediately as a solution, and here this is what you get as an energy efficiency, is 30.3 megabits per joule. Of course, you can play with these numbers, and my ex-postdoc, Emil, has software available where you can play depending on the cell radius you're taking, the different power amplifiers you're having, things like that. All that is available, and you can tweak the numbers. And you can find some other cases. When you do maximum ratio combining, MRC beamforming, and you force that, then you also find something where the optimum number of antennas that you should use is a base station with 81 antennas, serving simultaneously 77 users, this is the transmit power that you should use. And of course, the user rate goes down in that case, and it's the 2 PSK that you can use. That's the optimum thing. Now, what happens in the multi-cell setting? I did the clean slate approach in the single cell. Now, what happens if I want to do a clean slate approach for the energy efficiency in a network? Okay. The limitation that I had before was, of course, the fact that I had perfect channel knowledge and no interference from other cells. What I'm going to do, of course, is consider a multi-cell scenario where you have a lot of clusters, and in each cell you have a base station with antennas, and I'm going to design the number of users that I should simultaneously serve, the number of antennas that I should use here. So all cells look the same, jointly optimized. All cell transmits in parallel. I'm going to do fractional pilot reuse, divide cells into clusters, meaning that during the pilot transmission, I don't use the same frequency. And you know this problem comes from the problem known in massive MIMO called pilot contamination. Okay? I think you're quite familiar with that. And then you have uplink pilot length, T uplink K, for T uplink between 1, 2, and 4. So in that case, what happens, well, you can rewrite the things where you take into account imperfect channel knowledge to the fact that you have this pilot and interference coming in. Interestingly, you can have an expression explicit of the rate here that we wrote here. It's a bit tedious in terms of calculation, but you can get exactly, depending on the statistics of distribution of the users in each of the clusters, and also outside the other clusters, the expression of the rate here. Okay? And now, of course, my goal at the end, so this is due to pilot contamination, and here you have also what we call intra and inter-cell interference. Okay, so one of the big problems we have is, of course, that expression then to optimize it is a bit difficult. You don't have no closed form optimization in multi-cell case, but numerical analysis is still possible. You have that formula and you can play with that. Similarities and differences when you go in the multi-cell setting. Power consumption is exactly the same. Rates are smaller, upper limited by pilot contamination. Overly higher rates are not possible. And clustering fractional pilot reuse might be good to reduce interference, things like that. So what is the solution you get? The solution, quite remarkably, is the following that you get. If you want to do a clean slate design of a network completely using the energy efficiency metric, you get that the best thing you can do is to use a massive MIMO setting in each of the cell with 123 antennas and K equals 40. Which means exactly we're coming toward the factor that Tom Marzera has approached, meaning that you have at least a factor between 4, 5, 10. Here, the factor that you get is 3. Of course, if you change a bit the tweak and bad parameters, you can get to that factor 10. Okay? But that tells you that massive MIMO appears as one of the solution for zero forcing beamforming of the energy efficiency metric. Okay, and it's the solution when you consider the setting that we took into account for the modeling. Okay, if you decide to do different reuse factors for the pilot transmission, then of course you can get different energy efficiency and error throughput at least results. But I'm not going to go into those details to do it. Okay. So at least as far as this part is concerned, well, what we got is the following, is that you can optimize the energy efficiency, and you get that the energy efficiency is a quasi-concave function of MK and alpha, closed form optimal for MK or alpha for single cell, alternating optimization algorithm when you want to do it in the multi-cell setting. What's the most important thing is that massive MIMO appears as a natural solution here. Okay, fraction pilot reuse important. The more circuit power, there's more transmit power, and limits of MK circuit power that scales with M and K. So let's go back now to the beginning. If you want to optimize only the error throughput, it's small cells. If you want to optimize the average throughput, having constant throughput per users and minimizing the consumption of energy, then the answer is massive MIMO. Now let's go step by step and see also after what happens. Okay? So of course, for people who are interested in massive MIMO and never heard about it, but I think you heard about it because it has been pushed a lot in talks around 5G. As you can see here, we're considering massive MIMO in the setting of having 123 antennas and K40 users, because that's the solution we got, not the solution with the 400 users and 40 terminals. But in any case, I liked the approach of Tom Marzetta, because basically it tells you that when you look at the evolution of networks going from 2G, 3G, 4G, and 5G, 2G, 3G, and 4G was mostly networks where you had less infrastructure than the number of active users that you served at one moment. Meaning you had one base station serving 26, 64, 16 users. And in 5G, we're going in a realm where we're pushing the inverse, where we have much more infrastructure than the number of active users. You have much more antennas, as you can see here, than the number of active users at one moment. So basically you're pushing, and that's because, of course, the costs are going down, and a mobile phone, basically, or at least a smartphone, costs much more than a small cell actually now, in terms of what it incorporates. By the way, you have to know that the setting that I'm showing with 143 antennas, 40 users, is not something crazy. You have to know that in 3G UMTS, you have already systems with 3-sector antennas and with 20 antenna elements. Why? You have 10 antennas with 2 polarization that gives you basically 16 antennas. In 4G, you have also what we call these vertical arrays per sector, that you're seeing here, 4. You have 4 MIMO times 60, which makes around 240 antennas. So it's something that it's not totally crazy in terms of the factors that we had. What's the difference with these things and the massive MIMO settings is that, of course, we're looking at many antenna ports here. Okay, we have active antennas, we have current flexible beamforming, and multi-user MIMO with many, many users that you're doing at the same time. Okay. Of course, I think that Shlomo had talked about that. You could deploy also, and we consider also massive MIMO in this setting. If you consider the channels I wrote in a different manner, where you start deploying and doing remote radio heads, this can be considered also as massive MIMO. In that case, as I told you, there's only this expression here. If you want to tick with the result, what will change is only this this factor here, the lambda here. The lambda here is the relative distance of the antenna with the user. Okay. So if you put them all, then it's just one point in there. But if you put your antennas in different ways and you start coordinating them and looking at the coordination, then you get things that Shlomo has been showing, and looking at what are the ways to design these different linear, rectangular, cylindrical, and stuff like this cloud RAN approach. I'll jump out of this just to tell you that one of the main reasons that, of course, it was proposed is this asymptotic channel orthogonality, which was in some sense also validated by a lot of channel measurements. There are some papers from guys in Sweden that I encourage you to read, and also by Jacob also when he was at Stuttgart doing some measurements showing this IID behavior and the loss that you got, which is around 20% with respect to the classical result of Tom. Okay. Of course, by the way, I forgot to tell you, I looked in my case at this fractional pilot reuse to design my system. There's a lot of work going in this pilot decontamination that we did not take into account. You can look at this approach also and look at the optimal number of antennas. I looked in the TDD mode for 5G. There's a lot of work redoing what we did with FDD and looking at the energy efficiency and looking at the clean slate approach of how many antennas you should use at the base station and how many active users you should serve at a given time in the FDD mode, which Giuseppe, I don't know if he talked about it, has been looking at these things. Okay. Now let me look at the last point of my talk, which is the multi-objective network optimization, which is one of the big things, I think, which will be at the heart of 5G, considering all those metrics. Unfortunately, I just took 2 of those metrics, and I looked just at the average throughput and the energy efficiency, or reducing the consumption. However, there's many metrics at the same time that are being discussed, which is the delay, the number of active devices per kilometer square, and also the total throughput that you have. So unfortunately, we want those efficient operations with respect to all those objectives and see what's also the clean slate approach we can do in terms of design, taking into account. So that goes, of course, beyond my talk, because that's not anymore 5G energy efficient, but 5G in a whole manner. Okay. Now for that, of course, you need also to go back to the mathematics and look at how you do some kind of multi-objective optimization, okay, because that's the goal. So your objective is to maximize a function, okay, or let's say not even a function, we'll see what it is, but you need to have a lot of metrics, G1, G2, Gn, which depend on X, with individual user rates, area rates, energy efficiency. You have a resource bundle, what I put here, big X, which can be power, resource block, network architecture, internalized users, and you want to do a feasible allocation, okay? So that's exactly what you have as resources, and you're looking at exactly your attainable objective. Now, the conventional approach is to pick one of the metrics, let's call rates, and turn the others into constraints, okay? So the optimization problem becomes just to maximize one of the constraints, meaning maximize the rate, and put a constraint on all the other. The solution in general is a scalar number, so you're happy because you're maximizing this. The cons is, of course, what's the prime metric you're going to take and how to select the constraints. Which one are you going to put below? The multi-objective optimization technique, of course, considered to take into account all metrics at the same time and no order or preconception. So you want to maximize this whole thing subject to the fact that X becomes this distance. The problem with that, of course, you come up with what we call a Pareto boundary. Okay, I think you're quite familiar with that. You've been a lot of results looking at that, where, of course, when you prove a metric, you degrade another metric. So you have this, of course, compromise to do. This is, of course, something that people in economics and engineering are quite familiar. In communication theory in general, we're not, because we always want to get better, and we never want to lose something. But in general, there's no win-win solution because, of course, your metrics are in general not always aligned. But at one moment, when you start doing something better, then it decreases the other. Okay, you're not automatically in something that is, I would say, relatively aligned here, where at the same time you start increasing and you gain, and you don't lose that much in one direction. Let's say when you start going up. So one way of doing it, of course, it's an a priori approach. If you're interested to look at that, is to define some kind of function which takes into account all those constraints at the same time. Okay, and this is what people have been doing, and we did in some sense when we took the two. You remember, sum rate, average rate, and divided by energy, is to construct some kind of new function, which is either the sum performance, the proportional fairness, the harmonic mean, and the max mean fairness. Okay, and looking at with this new function here, then you try to maximize it, and you leverage the different things. The interesting part with this a priori approach, and it's been used a lot in the literature, is to maximize a function here, one function subject to the X belonging to your bundle. The interesting point is you get a scalar number, gives one Pareto optimal point, and takes all the metrics into account. So you get 1 point. Okay? So, for example, in my case, if I had to do it, well, I'm constrained with a resource bundle. So if I take in my case of a cell with different cells, base station, I have the number of users, which are constrained from 1 to m over 2, m with m to m over max 500, for example, and p to the power, p to the p max, which I have to do. Another example in 5G, where you need to optimize a lot of numbers, is exactly what I did right now, meaning you take the average rate, where you have the bandwidth, you have here the cost of training, and here you have the rate that you're doing, and you're trying, of course, to take into account the power consumption with all the factors that you get here. Okay, amplifier efficiency, fixed power, secret power per user, secret power per antenna, computing the zero forcing beamformer, and then your goal is to maximize the 3 objectives. I want to maximize the average user rate, air average, I gave you the expression, the total average rate, which takes into account the number of users and the area, and then also optimize the energy efficiency, which is Kr divided by P total. So I get these 3, and then put them in one single thing and do it. So that's what we've been doing, where you show that the area and user rate are conflicting objectives. Only energy efficiency can be provided at higher area rates, and different number of users. So what you get, of course, different possibilities where we're working on this curve, where when you increase something, you lose something. But this, you get it numerically. Okay? But this is something that is not something that you cannot use. For me, I would be happier if I get an explicit expression, but of course you can get it in a nice manner and put all those objectives and look at this multi-objective function. So for the last part, same thing. The code is available, and you can play with that, where we implemented some multi-objective functions, where you take the functions, and then you can play with these numbers. And of course, the result here, of course, I forgot to say, but the results here that you get in terms of number of antennas, whatever you want, will depend, of course, on the table that you get here. But of course, if you have some kind of other power amplifier or something, where is it? Oh, okay, sorry. Okay, it's too far. Okay, let's forget it. Let's go back to the end. Okay, but in case you get the table depending on your cell and other factors. Okay, I think I'll stop here. So my main conclusion is the following. As you can see, if you want to increase only the area throughput, okay, per user, then the optimal solution is small cell. And as I told you, this is something already that was revealed in 1976 in terms of result, and it was a bit forgotten just because of the cost of deploying. And now it came back because we're looking at, as you know, wireless backhaul, millimeter wave backhauling, stuff like this. And so it's some kind of solution we can take into account, and which seems, for me, quite reasonable for 4G. As far as 5G is concerned, where we're taking all these metrics and objectives that have been defined or are still actually being defined by different projects and people, and if energy is considered, then massive MIMO turns out to be automatically one of the solution or the solution to take into account. Okay. Now, of course, if you want to take into account the 5 objectives, then it becomes more complicated, and you get something else, which corresponds to what I showed you right now, which is a multi-objective optimization problem, and then you just get some numerical results telling you what you should do. I think I'll finish with that. There's a couple of papers I encourage you to read with my co-authors around what we did. The only thing I didn't mention here, because I didn't know the time we had, is the mobility part. Okay, as you saw, what we took is some kind of block fading, supposing that everybody was fixed and not moving during a certain time. It turns out that, of course, if you start taking delay into account and people are moving, then you can also take into account the energy consumption by mobility. What it means if users start moving, then of course the power that is used to transmit will vary according to his mobility pattern. And we've been deriving some mobility models taking into account how the users move and looking at how the energy consumption is made by the fact that users are moving. So if you say my users move during an hour, then based on the movement, then you can look at that. And that's one of the paper here, large system analysis of the energy consumption distribution in multi-user MIMO systems with mobility. Okay. And I think I'll stop here and answer your questions. Yes.
Okay, thank you, Mérouane, for this nice talk. Actually, the last slide you just before, with the publications.
Yes.
Edward gave yesterday a nice tutorial on the same topic, so that's yes. Really complementary, I think. So yes. We have time for a couple of questions. Is there any question? Yes.
So if I understood correctly, So you had those parameters, right, where you quantify like the power consumption by processing and so on, right? And you said you took those out of a table. My question, because I believe that if you design your system differently, you might get different parameters, right? So my question is, how sensitive are your results to what kind of parameters do you use in your expression?
So, good question. So, first of all, for the expression, the model is there. Now, of course, okay. So, you have this total thing, which let's say, let me put it back for the power consumption only. That's a good question. So for this thing here, this is the model where you have the evolution of in a quadratic form and all these different terms. Now these coefficients, of course, are things which depends on the material you have. And this can change dramatically depending on the number of antenna, the efficiency of your amplifier, stuff like this, yes. So this we took it on tables which are actually given at the moment on the energy, on the power, or say the efficiency of the power amplifiers that are given now, but in 2 years, 3 years, it can change. So of course, we have a code, I mean, Emil made it, available where you can change and look at the different robustness of these things. This I haven't looked at. No, but that's a good question.
So, Martin, you have a question?
And it's on his lead shopping webpage at the moment, the code.
If I remember it correctly, for your first results, the single cell results, you had the number of users were about, had approximately the same order of magnitude than the number of transmit antennas, right? And
Yes.
then in the second result, when you had the multi-cell setting, it was only 1/3.
Yes.
In all cases, you've assumed single antenna users, right?
Yes.
And why was this effect that you have to reduce the number of users? Because of the intercell interference, or?
Yes, because
how
of
did you model that?
this parallel contamination and interference that
Sure.
you get, yes.
Yeah.
That's one of the main reasons you get this loss, yes.
Mm-hmm. And how did this enter your expression, by pilot contamination,
Okay.
the objective function?
Well, we re-derived the SINR, taking into account the pilot contamination.
Okay.
And then in one of the expressions, I have to get it back, you re-derived exactly the rate, and the rate changes. You'll see right now. Yes. You have a lot of terms here.
Yeah.
And this GPC, you take into account also the pilot contamination.
Okay.
Okay?
So that's the reason.
Yes,
why.
that's the reason, yes.
And but what do you think? How do the expressions change if you now assume that we have like 2 antennas per user, or like some users with 4 antennas?
That's a good question, and it would depend on the processing that you do also at the receiver side. I
Sure.
don't know. That's a good question, yes.
Okay.
That's a good question, yeah.
Thank you.
Could you say something about the results when we introduce mobility? What would be the interesting things you get there?
Yeah, so it depends on your strategy if you take into account delay or not. If you take into account delay, then of course the best thing to do is to transmit when the user is close to the base station. Now, if you're doing a full packet and always transmitting to the users, then it turns out that the fact that users are mobile, okay, will change the energy consumption, of course, and it's better for you when they're mobile than when they're not, by the way, okay? Because it turns out that, as you know, for static users, the main bottleneck are the users which are on the cell edge, and they never move, so you have to use a lot of power to be able to provide them those average rate that you're targeting. When they're moving, you have some kind of averaging which helps you. However, if you take into account delay, meaning that you're able to transmit to the users and you need to send the packet within 1 hour, this is we didn't do, then of course you can combine some very sophisticated strategy, meaning that you transmit only when the user within that 1 hour is up to a certain distance from the base station. So you don't use that much power to serve him the packet. Okay, but this we didn't do that. But I think that would be the right approach if you take into account delay into account. Yeah. Now the problem that you're just one thing for mobility. That's why Aris Mustaka has helped us a lot. Is the mobility models are quite difficult, you know, analytically to work it out, because of course you have to suppose that the guy does not go from a cell, and if he goes from a cell, then you have this problem of handover. Okay, it becomes crazy. So either you suppose that all your base stations are connected and you're doing some kind of cloud round, and then there's no problem wherever he moves, but then it's a super big cell. But if you start looking at a cell-by-cell basis, it's a bit crazy because you have these boundary region constraints. So either you have these bouncing ray tracing models where you suppose he comes back and has to, once he arrives at the border, he goes back in the cell. But if you start supposing that it's really mobile, it's a bit complicated. So that's why Iris has helped us a lot on these tweaking models of mobility of users. Yeah. Okay. Okay, good. Thank you. In the field to develop the networks we know that are being developed right now. The reason fundamentally why I also insist, and you'll see also in my talks, that in 5G there's a lot of mathematics, is that we're quite stuck with the Moore's law at the moment. And if you look at how the progress of the Moore's law has been used. It's been almost used up, and we can't do better anymore. And it turns out that there's been some studies showing that at the heart of 5G networks, if you look at how the daily traffic in terms of increase is going to go, some people talk about a 100 factor, others 1,000 factor, depends on the talks you've been listening. Well, if you start counting on how you can save energy per bit through Moore's law, improve energy efficiency, you'll see that the fact that you use algorithms and less computation has a big part of it. And that's going to be one of the big things which are going to be there in 5G. And a lot of people are investing in what we call tools for 5G. And that's one of the reasons at the heart of this center that we're developing in Paris. And I hope we'll have collaboration with you guys around that lab. Okay. Now I'm going to start my talk about this 5G. So first of all, I'm going to do some introduction about what is 5G, what people are looking at, and what we're aiming. And then there's going to be 4 parts. The first part is going to be about what we call the problem formulation, system model, what kind of metrics we're dealing with, energy efficiency, rate, power consumption, what are we talking about. And the part 2 is going to be very interesting because we're going to optimize the network based on energy efficiency. We're going to look at how to design a clean slate approach of, I would say, 5G based on this metric, which we call energy efficiency. And you'll see that massive MIMO will appear immediately as one of the solutions when you start doing the maths behind. So it's not something that you impose, it's just that by doing the maths behind, then massive MIMO appears as one of the options to be able to provide that energy efficiency gains that you're looking at. Then, of course, we're going to talk about the solution that we're going to find, which is massive MIMO, how it is, the main properties and the optimal IDs. And then we're going to look at what's at the heart and one of the biggest problems in 5G, what we call multi-objective network optimization. As you know, there's a lot of constraints that we're looking at in 5G. It's not anymore about, so that's also something that you need to incorporate in your modeling whenever you start taking into account the user distribution in your network. Okay? Now, that was until 4G. What is 5G? Now, if you look at 5G, well, there are different expectations from 4G. It turns out that there's still some design objectives that are being defined at the moment, but these things, there's a lot of consensus around them. Increasing the average rate, even increasing the average area rate, having a number of active devices which increases, and having what we call also an energy efficient metric. So basically, instead of having just the increase of high data rate, it turns out that people are trying to cope with all these different combination of metrics and trying to impose a new clean slate design of the network based on these metrics there. Okay? Now, if you have that, how should you start? Well, you've been going through a lot of, I would say, plenary talks and overview articles around 5G, saying what it should be. But however, we still lack some fundamental, I would say, reasoning around that thing. Okay. So here, what I did is just recall the different objectives that people have imposed for 5G: higher user data rates, higher area throughput, great scalability, number of connected devices, higher reliability and lower latency, better coverage and with more uniform user rates, and improved energy efficiency. Now, if you want to incorporate a clean slate design taking into account all these metrics, it's a bit complicated, okay? And often these metrics are conflicting, meaning you cannot have a win-win situation for all the things. So my talk will start step by step. The first thing I'll do is just look at one of the criteria, which is higher user data rate, and look at what is the clean slate design that I have when I just impose a higher user data rate. And then I'll impose 2, and then I'll impose 3, and then we'll go forward until we'll start imposing all these constraints, okay? So if you start imposing the first one, well, that's going back into, I would say, the 4G constraint that we put in just having higher user data rate, okay? Now, if you look and you want to increase the data rate, it turns out that if you look at how, and these have been taken also by, these graphs have been taken by also some studies made by companies, and you look at increasing rates, there's a lot of different criteria, and it turns out that exactly in the same manner, mathematics will appear as one of the tools to be able to find a solution to that, okay? Okay, I think you saw many talks around these things, saying that, of course, there's a rapid traffic growth in the next years. A lot of factors, depends on the studies that have been made. Either it's Gartner, Cisco here that I brought here, showing it how you have this exponential increase in terms of traffic, and people are doing extrapolations, and that's one of the reasons we're looking at a new technology willing to sustain those increases in terms of traffic. Now, it turns out also that there's what we call Martin-Cooper's law that shows also how the traffic and data connections are increasing every, I would say, 2.5 years. And if you saw the Cooper's law, there's around a 32% increase per year. And with the new predictions, you'll have something around 61% per year, which shows you also that we're trying to aim something new. Okay. Now, if you look at how things have been designed before, usually people have been looking at what we call higher data rates. And that's at the heart of 2G. 2G was mostly voice, but let's say 3G and 4G then having a higher data rate. It turns out, of course, that if you look at that, the implementation and design was basically done by looking at how signal propagation was going on. And if you look at the way signal propagation is going on, then of course you have here at the heart of base station, and here you have cell edge. And then we had, as you know, in these 4G scenarios, a lot of problems in coping with people at the cell edge because these guys didn't have the right rates to do it. It turns out also that if you look at the spatial distribution of users, when you look at a network, the majority, unfortunately, of users are at the cell edge. Of course, they're not physically there. It's people who are connected. And you have to know that why a lot of users are at the cell edge in general is just because if you have a bad connection, then in general you stay there and you take that resource and you stay for long. So if you take a snapshot of a given cell, then you have some people at the cell edge more often than near the base station, because people are near the base station just take the traffic and they just go. Okay?
It's my great pleasure to welcome Mérouane Debbah after the nice talk yesterday of Gerhard Fettweis on 5G. Today it's another big guy of the 5G who will give this plenary talk. So let me just introduce Mérouane. So Professor Mérouane Debbah get his PhD from École Normale Supérieure de Cachan in France. From 2003 to 2007, he was assistant professor in Sophia Antipolis Institute Eurecom, and then from 2007 is a full professor at Supélec in France and holder of the Alcatel-Lucent chair on flexible radio, and is also recipient of the ERC grant MORE, meaning Advanced Mathematical Tools for Complex Network Engineering. He received many Best Paper awards, and in 2001 he received the famous prize, the IEEE Glavieux Prize Award. So it's my great pleasure to welcome Mérouane for this talk on the 5G energy efficient wireless design.
Okay, thanks. So I don't know. Okay, so I think I have to talk here because the thing doesn't work that well. So it should be fine. Okay, great. Okay, so first of all, thanks for coming this morning. I think the weather is excellent, and you should have gone to the beach and enjoyed the time there. But I'm very happy that you came to listen to my talk, especially as I had to prepare it. So at least there's something a bit of meat for you to listen to. So my talk is going to be about 5G energy-efficient wireless design. It has been mostly made by one of my postdocs, Emil Bjornsson, who's now moved to Linköping University and has got an assistant professorship there, and Luca Sanguinetti, who has a Marie Curie Fellowship and who's working also in my team within Supélec. So as far as I'm concerned, you have to know that I'm a specialist of random matrix theory, and I've been working since 7 years at Supélec through an Alcatel-Lucent chair on flexible radio around the topics of random matrix theory applied to wireless communication, as far as I would say asymptotic design is concerned. And we've been using that tool in a very efficient manner to understand better how 5G massive MIMO small cell networks could be deployed. Another third of my activity these last 7 years have been around game theory, applying tools for, I would say, defining self-learning algorithms for small cell networks. Another 1/3 of my activity has been on the use of what we call software-defined radio tools to be able to implement those things, and we've developed some cards called SDR cards. Now I have to make a bit of publicity. It turns out that starting September, I'll be joining Huawei and opening their French R&D research center, which will be around the Mathematical and Algorithmic Science Lab. And the objective of that lab is to provide some new ideas around 5G using mathematical tools. So we're looking to recruit 70 top mathematical experts in that field. So if some of you are interested to join in, I'll be very happy because we have to fill those positions by the end of the year, meaning end of 2014. The topics that we're looking at for your information and we have identified are these topics that you see behind. So we're looking at experts using random matrix theory, free probability theory, stochastic geometry, discrete mathematics, statistics, game theory, mean field theory, information theory, signal processing, queuing theory, estimation theory, decision theory, probability theory, optimization theory, statistical mechanics, factor graphs, control theory, learning theory, partial differential equations theory, and optimal transport theory. Now you can ask me why we're doing that. Well, basically, it turns out that in 5G, and that's something that Bell Labs has also been doing since the late 1880s, is that you cannot define new, I'd say, algorithms and new ideas just by trial and error. And so mathematics is at the foundation of developing new ideas, and that's something that Bell Labs and then AT&T found useful by bringing the top experts